Okay, I'm going to talk rather quickly here because I want to try to wrap everything up in this one last video. So we have just been talking about the shape of a distribution, but in terms of describing a histogram, so when you're given a histogram and if we ask you to describe what you're seeing in that distribution, we want you to touch on a few different things. So obviously we want you to focus on the overall pattern, any striking deviations from that pattern. So when we talk about that, we mean what's the overall shape? Is it skewed? In what direction is it skewed? Is it symmetric? Does it have some other type of shape? Are there any outliers? So are there any observations that seem to fall outside the overall pattern? Any values that are off by themselves, far away from the rest of the pattern? We'll look at some examples of that shortly. We also want you to be able to look at a histogram and tell us something about center and variability. So you'll soon learn that there are formal ways to measure center and variability. We'll get into that in chapter 12. But we want you to be able to look at a histogram and just give a general judgment of where you think the center is and what you think in terms of variability. So in terms of the center, when just looking at a histogram, we mean, where does the midpoint seem to fall? Where does the middle seem to be of the distribution? Variability, what does variability mean? So variability has to do with the overall range of the data. It has to do with maybe where most of the data is falling. Maybe the overall range is from 0 to 100, for example, but maybe most of the data is falling between 50 and 80. So again, you're going to learn soon that there are formal ways you can measure variability and different measures you can pick out depending on what you want to say about the data. But again, we want you to be able to look at a histogram and just make some informal judgments of where you think the center is and what you think in terms of the variability of the distribution. So let's look at an actual distribution and spend some time talking about what this looks like, describing this distribution. I thought this distribution might be interesting to many of you. At Chipotle, how many calories do people eat? So my husband loves Chipotle. I'm sure many of you like Chipotle, maybe eat there quite often. Sadly, it's not good for us. Well, it depends on what we want to eat, but quite a bit of it's probably not good for us. So if you plan to eat there, that might be your big meal of the day. But I really loved this news story because they showed a histogram. So you don't often see histograms in newspapers. This was in the New York Times. So you can see that the calories in a single meal at Chipotle are pretty high up there. You're getting almost all of your daily calories in just maybe one burrito from Chipotle. But let's say we wanted to describe this distribution. What are some things that we could say? And then I encourage you to go and look at the article. You can learn a little bit more. They give you some tips about how you might want to eat, what you might want to order if you don't want to consume a lot of calories. And they have a really interesting section in the article about how they gathered their data. So I think that would be really interesting to look at. But look at this distribution and how would you judge maybe what the shape is? Well, again, let's imagine a smooth curve going over the distribution. I would say that the distribution is a bit skewed to the right, so the tail's pointing off to the right. So if we didn't have, this whole chunk over here, I would say it's more symmetric. But obviously there are some meals that have lots and lots of calories. So that's pulling the tail off to the right, off to the larger values in the data set. Where does the center seem to be? Well, I would say it's probably somewhere in here, somewhere close to maybe 1,000, between 1,000 and 1,200. Variability. So variability, again, remember, has to do with differences in our data set. If we have no variability, it means everybody's the same. And obviously there are lots of differences. Not all of the meals have the same calorie content. We have down here as little as maybe 100 or 200. So hopefully you can see that where the x-axis starts, all the way up to more than 2,800. So there's an overall range of maybe between, I would say maybe between 100 and 3,000. So it's a little bit hard to judge based on how the x-axis is labeled here. But clearly a large overall range of values. Most of the data, however, seems to fall within here. I'd say, a bulk of it is maybe between 800 and 1600. So again, when you're just looking at a histogram and trying to tell us something about center and variability, there's not necessarily one right answer. We're not looking for everyone to say, for example, the center is 1,000 or the center is 1,100. There can be some wiggle room there. We just want to make sure that you understand what it means when we ask you to describe the center, describe the variability. We want to make sure you know the difference between those terms. Here's a couple other histograms that were in that same article. So the news gets even better here. They looked at all those same orders, and they looked at the milligrams of sodium per order, how that compares to the recommended daily allowance of sodium. They looked at the grams of saturated fat. And again, we can see here with sodium that, again, I would say that's probably slightly skewed to the right. Almost symmetric, so not terribly skewed. Obviously, with the fat grams, we see a distribution that's skewed to the left. And again, skewness is based on where the tail points to as you're looking at the distribution, the direction that the tail is pointing off to. Okay, so outliers, we want you to have an understanding of what an outlier is. So an outlier is a value that falls away from the rest of the pattern. So it can be an unusually large deviation, it can just be a minor deviation, but it's something that's obviously different from the overall pattern. It's a value that sort of stands out against the main pattern of data. So how can we spot something that's an outlier? How do we know if we have an outlier? So here again, you might remember that graph I showed earlier of the difference between the winning and losing points of the Super Bowl games. Do we have an outlier here? Well, you might be noticing that we have a little gap here, and then we have this value over here that's falling away from so here's the overall pattern, and this is clearly falling away from the pattern. Is that an outlier? Would we say that that's an outlier? When we get into chapter 12, you'll learn that there are some ways that you can engage in some calculations to determine if something is actually an outlier or not. Whether it's an outlier is based on how far away it falls from the middle of the distribution. So, but I would definitely say that, this value is kind of standing off by itself. So it does seem like it's unusual. It's different than the others. There aren't that many values that are that particular value. What do you think you should do if you have an outlier? And how will it affect your interpretation? So we're going to get into some of this now, and we'll talk more specifically about this when we get into chapter 12. But you always want to be on the lookout for outliers. They will affect how you describe the data. They'll affect measures of center and variability that you compute. And they could affect how people interpret the information. You don't want to just throw them out. Sometimes you do, but we want you to be able to critically evaluate why something is an outlier and to think about what is the best course of action depending on the particular circumstance. So here's something I want you to think about. So one semester, we had a survey of STAT 1350 students. We gathered a lot of information from them. And here is a variable that we, you don't see the name of the variable. I want you to try to guess what's being displayed here. Well, you'll see most of the values here are between maybe 3 to 4 and maybe 12 or so. But then we do have some values way out here. So this is a quantitative variable. We asked students a question, and these are the responses we got, and we graphed this information. Clearly there's this strong skewness to the right. What do you think is being displayed here? So again, maybe pause a little bit, take some time to think about it. Okay, so again, in autumn 2014, we did a survey. Here was the question. On average, approximately how many hours of sleep do you get per weeknight? Okay, so wow, there are some students who are sleeping 40, 50, or more hours per weeknight. Most of them are sleeping maybe between 4 and 12 hours. That seems to make sense. Where the average might be somewhere around 8, 7 or 8 or 6. So obviously, you cannot sleep more than 24 hours in a particular day because there are no more than 24 hours in a day. So obviously, these values were errors of some kind. Maybe students misread the question. Maybe they thought it was asking about how much sleep do you get in a full week. We're not really sure. But these are not legitimate values given what we were asking them, given the question we were asking them, because values cannot have those, or you cannot sleep that much in a particular night. So what should we do in that case with the outliers? Well, that's a particular case where it makes sense to exclude those numbers from the analysis, to remove them, because they're not legitimate. Nobody can sleep more than 24 hours in a given day. You can't even sleep 24 hours in a night. A night is not 24 hours long. So, and again, why did we see those values? We don't really know, but we know they're not legitimate. So we have justification for removing them. But that's not always going to be the case. You might have outliers where it's legitimate that you could have that particular value, and it doesn't really make sense necessarily to just throw it out. It makes sense to tell your readers about it, to let them know, there's an extreme value and that's affecting our other measures, and to maybe explain why you think that you have that value, why it's so extreme. But unless it's a data error or a measurement error that you know about and can't fix, you're not justified in removing that value. So we don't want you to think if you have outliers, you can just throw them out. It depends on why they're outliers. And outliers can sometimes be very good. And there's an article I linked to here that I encourage you to look at. It's about people that seem to respond differently to certain treatments, or maybe they live a lot long. They have a disease and they live a lot longer than others who have that disease. And by studying them, we can learn more about those diseases and about treatments for certain things. So sometimes outliers are really great. So just because something's an outlier doesn't mean it's bad, doesn't mean we should get rid of it. So that's the main point that we want to drive across here. We want you to be on the lookout for outliers. We want you to know how they impact things, but we also want you to know that you don't just throw things out without any justification or reason for doing so. Okay, so I thought I could get through this quickly, but I do have well, actually, I'm just going to kind of quickly show you what's at the end here. I don't know that I need to talk too much about it, but bin width is something to think about. I'll let you read this a little bit later on, but bin width has to do with the width of the intervals here along the histogram, and we just basically want you to know that as you start changing that width, you're going to change what the distribution looks like. So that's something that you want to think very carefully about. This is discussed a bit in chapter 11, but just as with your bar graphs, you want to look really carefully at what's being plotted along the x-axis and how wide the intervals are, because that can change the overall appearance of the distribution. I'm also including here just kind of side by side how histograms and bar graphs are similar and different from each other. A lot of times I'll see students talk about a histogram and say that it's a bar graph, but remember, bar graphs are for categorical variables, histograms are for quantitative variables. With histograms, we order things in a particular way from smallest to largest. With bar graphs, remember, it doesn't really matter what order your bars are in. You can change that around. In both cases, the bars are similar in terms of width, but again, one of them is for categorical data, one is for quantitative data. And then finally, just more histograms in the news. So I came across this news report. It was from the Pew Research Center. And basically, they had these graphs and they referred to them as histograms. And I was kind of curious as to why they called them histograms. I wanted you to look at these and tell me if you think they're histograms. Note along the x-axis, we're categorizing people as being liberal, mixed, or conservative. And we're looking at how the percentage that fall in those different categories. they call these histograms. I think, this was based on some sort of 10-item scale that people completed, so they didn't actually put the scores that they got here along the x-axis, but they didn't put the scores that they got along the x-axis, which probably would be better if they want to call this a histogram. And obviously you don't see really the bumpiness of the different bars here. They kind of try to smooth it out a little bit. But in any event, I just thought it was kind of interesting that they were using that term histogram when we think of histograms as being different. We think of the x-axis as being quantitative. We think of the bumpiness in terms of the different bars rather than having this smooth curve. Okay, so again, that's what I wanted to say about Chapter 11. We hope you'll ask questions if some of this is not clear, and then when we get into Chapter 15, or Chapter 12, we will talk about more formal ways to measure center and variability.